Now we are ready to start discussing the electric potential. Before I start discussing the electric potential, let me just make you get a feeling of the fact that the electric field also, like the gravitational field actually, has, when there is a charge in it, it has potential energy. Okay, this system of electric field plus a charge in that electric field has also potential energy, just like gravitational field of the Earth plus a mass has one. So think of a given charge distribution that is generating some field in space. Okay, assume that the field is directed in this direction, to this way. Now bring a point charge and throw it against the field. Now the point charge will start with a given kinetic energy, so a given speed. Now since it's moving against the field, and since it's positive, the force will be against its direction of motion. Okay, so what will happen is that as you throw this charge, it will move, but it will start to slow down, okay, losing kinetic energy until it reaches a point where it will come to stop. But it will not stop and stay there. Then it will start to speed up again and move with kinetic energy, gain kinetic energy again. Okay. This is like what? This is like when you throw a stone upwards. The stone starts with a given kinetic energy with a given speed. It goes up until it comes to rest temporarily, so losing all its kinetic energy. Now you learned and you know now that all this kinetic energy has been changed into potential energy, and this potential energy is given again, and this kinetic energy is given back once this starts going down, because as it goes down, the kinetic energy, the potential energy decreases and the kinetic energy increases. So when you throw the stone up, the kinetic energy that has been lost was transferred to potential energy, and this potential energy was given back as kinetic energy. The same applies for the charge. When you throw this charge into the field, the charge moves, losing kinetic energy, but this kinetic energy does not go out of the system. It is still in the system of electric field plus the charge. It's stored as potential energy. It reaches a point here where it stops. So all of its kinetic energy has been changed into potential energy. Now it starts moving back again, and so it starts gaining kinetic energy again. So the kinetic potential energy that has been stored in the system is given back again. So it decreases, the potential energy decreases, and the charge, the kinetic energy increases again. Okay. So this is, as you can see, makes it clear for you that there is similarity between a charge in an electric field and a mass in a gravitational field, and that we have somehow a potential energy for an electric field and a system of electric field and a point charge in that electric field, just as we have gravitational potential energy for a mass in gravitational field of the Earth. Now we will define precisely this potential energy, find expression for the potential energy, and also we will define something that we did not define in the case of gravity, which is the electric potential. Okay, so let's start from basic principles. If you have a test charge placed in an electric field, then that test charge is Q naught. Q naught can be any test charge. It's a small point charge. This is what we mean when we say a test charge. It will feel a force, electric force, given by the charge multiplied by the electric field. This is something that we know. Now this force is conservative. Okay, we know that the electric force is conservative, and so keep this in mind. The meaning of this, in view of what we have said, just reviewed in the last class, is that there is a potential energy associated with this force, and this is what I have demonstrated at the introduction by drawing your attention to the similarity between the gravitational potential of the gravitational field and the electric field. Now, so we know this. Now assume that you have this situation. You have point A here and there is a point B here. It didn't come out. So if the particle moves from point A to B, if the charge moves from A to B here, point B should be here, okay, then in this case, what's happening is that if there is an external force that is doing work on this charge to move it from A to B, then in this case, so that it moves from A to B, but without changing the kinetic energy of that charge, then in this case, as we have learned in the previous class, the work done by this external charge, external force, is equal to the negative of the work done by the field. Okay, that is W external is equal minus W electric field minus W internal minus W electric field. Now, here, as this charge moves from here to here along this path, ds, you divide this whole path. If you want to find the work, you divide this whole path into small ds's, okay, and ds is the displacement, and in this case it will be tangent to the path. Now, what is the work done by the field in this case? As the particle moves a given ds, a small infinitesimal ds, then dw, the work done through this ds, is this f dot ds, the work done by the field in this case. Q0e is the work, is the electric force. Okay, so it's f dot ds, electric force dot ds. Now, this is the work, the field is an internal force. Okay, so the electric force is an internal force, and therefore, when an internal force does a work, then there is a change in the potential energy, and this change is negative. W internal is equal minus delta U. So here it is dW, so because it's a small infinitesimal work, therefore there is an infinitesimal change in the potential energy equals minus this, minus dW, minus Q naught E dot ds. This is the force dot ds, so it's minus this. Okay, this is by definition. Now, what is the work done as this goes from A to B all the way? Well, we have integrate, we add up all the dW's, okay? And what does this mean? You will carry out the integral. I have taken Q naught outside the integral because it is just a constant point charge. So this is the minus sign, that comes from here because of the definition of the du equals minus W. And you carry out this integral. So this says that the change in the potential energy as the charge moves from A to B is equal minus the work done by the electric field. Minus the work done by the electric field. This is what does this relation tell you. This minus sign has nothing to do with the fact that this is minus or positive. No, it comes from the definition. Okay, so this is an important. So this is a very important relation. This is the electric counterpart, if you like, of our relation, that is delta U gravity was equal minus work gravity. Here it says delta U, the change in the electric potential energy of the charge field system, charge Q naught in the electric field, is equal minus the work done by the field, minus work done by the field. Q0e is the force dot ds, so the whole integral is the work done by the field on the charge as it moves from A to B. Okay, this is what does this say. Now, the electric force is a conservative force, just like gravity, and so the meaning of that is that this work done as the charge Q naught moves from A to B in the field is totally independent of the path that you use to take the charge. So if Q naught goes along this path, this path, this path, this path, this path, wherever it goes, when you calculate this work, the result is the same. It is just UB minus UA. What is UB? So I'm defining a potential energy here. What is UA? I'm defining a potential energy here. So this actually tells you, is also acts to define the potential energy in a field. Okay, I say that I have a potential energy here. I have a potential energy here for the charge Q naught field system. Okay, the difference in as the charge moves from this point to this point, regardless of what is this path, there is a change in the potential energy. This is equal to, and this change is minus the work done by the field. Okay, and that's all. And so this quantity should be independent of the path, because whatever you do, it will boil down to the change in the potential energy, or minus the change in the potential energy. This is exactly the same as in the case of gravity. This integral, this type of integral, is called line integral or path integral. Now we move to another quantity, not the potential energy, but the electric potential. Now this is a concept that we have not introduced in the case of gravity, but we introduce here, and it is one of the most crucial concepts actually in electricity and magnetism. Usually in real life applications, the potential, or with its more common name, the voltage, is the crucial quantity, and probably you are familiar, all of you are familiar with this. So the potential energy per unit charge is the electric potential. So if you have potential energy, we have seen that each point in space will have a potential energy if you have a field charge system. Now, if it moves to another point, there is another potential energy. The difference in the potential energy is minus the work done by the field. Okay. Now, what we do here is we define another quantity, which is the potential energy per unit charge. So this is now independent of the charge, and we call this the electric potential. So electric potential is U divided by Q naught. That is the potential energy per unit charge, because you are dividing it for the charge. So if you have a point, for example here, this has UA is the potential energy of this Q naught here. The potential at this point here is just U divided by Q naught. Okay, so it is V, the potential at this point. UB is the electric potential of the Q naught when it is here. Okay, if you divide this UB divided by Q naught, it has units of joule per coulomb. In this case, it will be the electric potential at this point. Okay, so now as such, since you are dividing here by Q naught, then you are eliminating the effect of Q naught, and so what remains is the fact that the potential is a characteristic of the field. It doesn't depend on Q naught. You are dividing Q naught out, and so this is only normal, and therefore this potential is actually a function whether when you have a field at each point in space it has a given value, and it is independent whether you have Q naught there or not, or any Q naught, or whatever is this Q naught, whatever is the value of this Q naught. Okay, so this is the electric field. It is like the electric field. The electric field, as you remember, it's a function of space. It's a quantity which has different values in space. Okay, when you have a charge distribution, you have an electric field. The space is no more empty space. There are electric field at each point. This electric field has a magnitude and direction. Now the potential is something similar, except now it's a scalar, so it doesn't have a direction. So when you have electric field, points in space now there is a function which is the electric potential, which has values at different points in space, and this value is a scalar now. It doesn't have direction. Now if you want to find the potential difference between 2 points in the field, then you just find delta U divided by Q naught. Now what was delta U? Delta U was this integral. So when you divide this delta U by Q naught, because the potential difference is the potential energy per unit charge, when you divide it by this Q naught, you end up with what integral? You end up with this integral, delta U over Q naught. That is the potential difference between any 2 points in space is minus integral from a b e dot ds. This minus sign comes from the definition, and this is the most general expression for the electric potential difference between 2 points in space. And as you can see, it depends only on the field, because Q naught is cancelled out. Okay, so Usually, like in gravity, you remember when we talked about, when we discussed gravity in mechanics, we say that the zero of the potential energy is irrelevant. What matters, the physical quantity, is the difference in the potential energy between 2 points. Now the same applies here. Actually, the meaningful and physical quantity is the difference in potential between 2 points in space, not the absolute value of the potential at a given point in space. And therefore, usually we take some arbitrary point and say, okay, the potential is 0 at this point, and we measure the potential of everything else with respect to that point. Just as we used to do in the case of gravity, we used to say, okay, we take the potential energy to be 0 at this level, which was completely arbitrary, and we measure the potential energy difference with respect to this level. Now, the units of the potential are the volts, V, and the volt is just joules per coulomb. So it has a different name. It has its own name. The potential has its own name, and it is measured by units of volt. This is where voltage comes from. Again, this is repeating what I said, saying that here the important thing is, again, to understand the difference and to be able to distinguish between potential and potential energy. Potential, you need the field to have potential because it is energy per unit charge. It's independent of the charge. So you have 2 points. You have a field in some region, point A, point B. There is a potential difference between these two, regardless of whether you have other charges moving or not. Okay. So the potential is a characteristic of the field, and the potential difference between 2 points depends upon what is the field in the region where these 2 points lie. However, to define the potential energy, you need a system field plus charge inside it. Okay. So this is an important point. So for potential energy to exist, there must be a system of 2 or more charges. In other words, you must have a field generated by one charge or another charge distribution, and it should be another charge or charge distribution in that field. In this case, you have potential energy. Like in the case of gravity, you need a Earth plus mass in order to have a potential energy. For the potential, no. You need just a source, charge, or charge distribution that generates for you a field, and the potential exists because there is a field there. Okay? So this is something important and crucial. Now, we have been talking about gravitational electric potential. Started with electric potential energy, and we said, okay, in this case, we will define something that we did not define in the case of gravity, which is the potential. But one might say, why we didn't do that? I mean, one might say, well, is there a gravitational potential? Can we define gravitational potential? Of course. Now, I will discuss this. I'll show you that what is the gravitational potential, but probably by looking at this, and, which is easy for you to digest maybe, you will understand what do I mean by the electric potential, which is potential energy per unit charge. So, do we have a gravitational potential? The answer is, of course, you can have it. How we define it? Now, the gravitational potential energy near the surface of the Earth for the Earth mass system is this. Okay. So, gravitational potential is the gravitational potential energy per unit mass. It is this divided by S. It is Gy. So, if I have a mass here, I take my zero of the zero of my potential energy in gravity here. I put the mass here. At this point, the gravitational potential energy is mgy. Now divide by m, you get gy. Okay, but why? So this is the potential. Now y is arbitrary, can be any value. Therefore, actually, for any y, g times y, okay, is the gravitational potential energy per unit mass. In other words, how much potential energy per 1 kilogram you will have if you put a mass there. Okay, so this is the idea of the potential. Note that this has nothing to do, it doesn't depend on the mass that you are putting there. Okay, it just exists because you have an electric field existing. the potential difference will be delta V. If you want the potential difference between this point and this point, okay, you find potential at this point minus the potential of this point. You just gy final minus gy initial. This is the difference in the potential between these 2 points, and it is just the potential difference. So in gravity also you can find the potential difference. Now the potential, if you know the potential at any point, you can think of it this way: I know the potential at any point, which is the potential energy per unit mass. Then if I bring a mass, whatever is that mass, and I put it at that point, multiply that potential by the mass, you get the potential energy of the mass in the gravitational field of the system. Now it's the same idea like in the case of electric charge. You have electric field, you have potential everywhere. It's a quantity which varies from point to point in the field. If you want to find, if you have a point charge and bring it into the field, you want to find the potential energy at that point charge in a given point, okay, put it at that point. If you know the potential energy at that potential at that point, that is potential energy per unit charge, multiply it by the charge, you get the potential energy now when this point charge is there. The same as gravitational potential energy. I know the potential at this point, gravitational potential at this point is just dy. Bring any mass, 5, 10 kilogram, whatever, put it here, multiply this by the mass, multiply gy, which you know, by mass, you get the potential energy of the mass in the gravitational field. Okay, so this is the idea of, this is gravitational potential, similarity to electric potential, and the idea and the relation between potential and potential energy. This leads us actually to viewing the potential as an energy tariff of space. I used this before when I talked about the electric field. I said we can think of the electric field as a force tariff of space. Here, the gravitational potential can be thought of as an energy tariff of space. What does it mean? You know, the potential function, if you have some source, then the space now around that source has an electric field. Okay, so it's different than the field before you put that source. Okay, so there is something new in the field, in the surrounding, in the space surrounding that charge distribution, and which is what? Well, there is electric field, and as a result, we have electric potential. And so, what we say is that once we have electric field, then each point in space, I can assign it a tariff for energy per unit charge. Now this assignment of tariff, this tariff of energy per unit charge for all points in space is the electric potential. Okay, the meaning of this in this case, each point in the space around this charge distribution, and in other words, each point in a space where I have an electric field will have a tariff telling you how many joules per coulomb of energy that point has as a tariff. Okay, this is just the V. Now V here is a function of space because this tariff changes from a point to a point, depends upon where you are in the field. So the whole space will have this tariff. Each point in space will have this tariff, which is how many joules per coulomb I have assigned point in space, every point in space. Okay. Now, if you know the tariff, bring any point charge, put it at that point in space. If you know the tariff, just multiply it by the charge with its sign, positive or negative. You get the potential energy of that charge when it resides there. Okay. So you get the energy of that point charge because you know the tariff. What is this tariff? It's the potential. So it's just the potential of a point charge placed at a given point in space is just that charge multiplied by the value of the potential at that particular point. What about if your point charge was here and I moved it here? Okay, what is the change in energy? Okay, well, what is the difference in tariff between this point and this point? This is delta V. Multiply this difference in tariff by Q, which is the charge that has moved from A to B, then in this case you get what is the change in energy. So the change in energy is just change, charge multiplied by the change in the tariff of energy tariff of this space in this charge between these two points, and it is just this relation. Now this relation is a very important and a crucial relation in electrostatic. Actually, it's one of the fundamental relations that you have to know and understand. It says that if a charge moves an electric field between 2 points, then there is a potential difference between these 2 points. That is, there is a difference in energy tariff between these 2 points. Then the change in the potential energy of the system of this charge in the electric field is just Q, the charge, multiplied by delta V. I'm talking about point charge here, of course. So this point charge multiplied by delta V. Now this point charge can be positive or negative, so you substitute it here along with its sign. You substitute it here along with its sign, so it's important. So this is one of the fundamental relations that you should know, understand, and be able to apply comfortably. Of course, this whole thing can be positive or negative, depending on whether delta V is positive, negative, or charge Q is positive or negative. Okay, it doesn't matter. It can be anything. It can be zero also if delta V is equal to 0. If the 2 points where the charge has moved is the same, are the same potential, then in this case that will be that point charge. The potential difference between these 2 points will be 0, and so there will be no change in the potential energy. There is, as I said, another name used for potential, which is, especially in applications engineering, they use the voltage. Okay, so we say that you have a device. What is the voltage? Well, the voltage applied to a device or across a device is actually the potential difference between across that device. Okay, so the word here, voltage, is the same as the electric potential across that device. So voltage means potential difference actually. The voltage is just, you know, a change in the energy tariff between 2 points in an electric field. And it is not something that you give to a device. I mean, when you connect it to electricity, you are not giving, injecting voltage into it. Okay, no, you are creating an electric field. In this electric field, these are 2 points, and there is a potential difference, which is potential energy per unit charge between these 2 points. So as charges gets transferred, that is, as current flows in the device, then charge is moving from one point to a point, and say there is a change in the kinetic energy and the potential energy of the charges, and this is how you this change in the potential energy is what gets transferred to other points of to other forms of energy, and this is how you transfer energy to a device. But the idea is that this voltage is nothing but a potential difference across the device that is used. There is another unit of energy other than the joule that is used, especially when you are talking about at the atomic scale. This is electron volt. Look, although it looks like volt, it is not a unit of potential. It's a unit of energy. Okay, and the meaning of electric volt is that if you have electric field, okay, and there is a difference, 1 volt difference between 2 points. If a charge has the charge E, which is the charge of electron or proton, moves across this potential difference of 1 volt in the field, then the change in its potential energy is 1 times the charge. What is the charge? 1.6 times 10 to the power minus 19, and therefore 1 electron volt is equal 1.6 times 10 to the power minus 19 joules. So it is energy a charge field system gains or loses when a charge of magnitude E is moved through a potential difference of 1 volt. Okay, so this is a small quantity, but it is important at the atomic scale. There are kilo electron volt, there is mega electron volt, giga electron volt, even giga electron volts.